Welcome back. In this lecture, we will continue with our discussion of the scale factor approach. We will do more examples in where we obtain modeling and prediction rules using the scale factor approach. Similarity requires that not only the total forces on the prototype and the model elements be scaled by a unique scale factor, which depends upon the scale factors for mass and acceleration. But the same factor must also scale every component force that make up the total force vectorially. This is what we discussed in the last class. So if a pressure force, viscous force, and a gravity force make up the total force, then within the prototype and the model, there would be the same scale factor, and each component would have the same direction, and the magnitude of each component would be scaled by the same scale factor Kf. The process that we outlined for obtaining the modeling rules consisted of identifying the various force components that determine the net force at a point in the flow field, then obtaining the scale factors for each of these force components using the physical laws that govern the phenomena. Then equating the scale factors so obtained to the net force scale factor Kf obtained from Newton's law of inertia. This is termed as the inertial force factor. And then obtaining the non-dimensional pi numbers in terms of the characteristic independent quantities from the relations established in the step 3 above. These give us the invariants that establish the modeling rules. As we did in the last class, we first obtained the relationships among the scale factors for each of the forces and then wrote down the corresponding pi numbers. For example, the total or the inertial force Fi is governed by the law that this is equal to mass times acceleration. In writing the scale factor for mass in terms of k rho and kl, and for acceleration in terms of kv and kl, we get the scale factor for the inertial force as k rho kl square kv square. And from this, we obtain that the inertial force divided by rho L square V square is the relevant pi number, which should be invariant between the prototype and the model. In this and in all subsequent discussion, the characteristic nature of these quantities is understood. Similarly, we derived the pi numbers for the unsteady flow, for the viscous flow, for the gravity force, and for the pressure force. For surface tension force, for the compressibility force, and for the centrifugal force, which is mass times omega square r. We equate the scale factors for the various component forces for obtaining the modeling rules. So, for example, if we equate the scale factor for the inertial force and the viscous force, we get this relation among the scale factors for the independent parameters. And then from this, we can write rho VL by mu as an invariant. Of course, this is recognized as the Reynolds number. If rho, V, and L and mu are the characteristic quantities for a given flow. In fluid mechanics, if we take the ratio of the inertial and viscous forces, that is, we equate the scale factors for inertial and viscous forces we get Reynolds number. If we equate the scale factors of inertial and gravity forces, we get V square by GL, which is the square of the Froude number. Similarly, the Euler number, Weber number, Cauchy number, Mach number, and Struve number. This was all done in the last class as well. Let's do an example in which we match the Froude number. A seaplane is being designed for a takeoff speed of 100 kilometers per hour. Model tests are to be made on a 1/10th scale model. So KL is 10. The length scale factor is 10. At what speed should the model be towed to simulate the takeoff condition? And then the force required to drag the model seaplane through the takeoff is 9 Newton. Predict from this the thrust needed by the prototype at takeoff. So, we identify the forces. Clearly, inertia is an important force, and in this case, the only other force that is dominant is the gravity force. So we use two laws. The inertial law, Fi is like ma, and the gravitational law, that the gravitational force Fg is like mg, where m is the mass. We write the appropriate scale factors relation. Mass scale factor is k rho kl cubed, and acceleration is kv square by kl. Similarly, for mass and gravity. And from these two laws, by equating this scale factor to this scale factor, we get kv square by kl, kg is 1, from which the pi number obtained is v square by gl, which is recognized as the square of Froude number. So, the similarity requires that the Froude number of the prototype flow and the model flow match. So, the modeling rule becomes Vm square divided by Gm Lm is equal to Vp square divided by Gp Lp. Clearly, Gm and Gp are the same. Lm by Lp is 1 by 10. And if we plug in the relation and we plug in the value of the prototype as 100 kilometers per hour, we get the model speed required for similitude to be 31.6 kilometers per hour. If we tow the model aircraft at this speed, then the gravity forces and the inertial forces would be similar, would have the same ratios, and hence the similitude is assured. There are no other important forces. And then, to determine the scale factor for thrust, we note that K thrust is like any other force. A thrust is like any other force. So, the scale factor for thrust would also be equal to the scale factor for any other force, and we choose the inertial force for simplicity. And so, the K for thrust would be K rho, KL square, KV square. And converting it to a pi number, we get thrust divided by rho, L square, V square is invariant. That is, it has the same value for the prototype as for the model. And from this, the thrust of the prototype is obtained as 9 kilonewton, 1,000 times more than the thrust for the model, which was 9 Newton. Let's take another example. A 1/6 model of an automobile is to be tested in a wind tunnel at a speed corresponding to the prototype speed of 60 kilometers per hour. Determine the model speed for similitude. Then, if the drag on the model at that speed is 510 Newton, what is the drag on the prototype and what is the power requirement of the prototype? What power would be required by the prototype at a speed of 60 kmph if the drag on the model at the corresponding speed is 510 Newton? So as before, we decide on what are the important forces, and we realize that in this model, where there are no free surfaces involved and where there is no characteristic pressure difference, the only forces that need to be modeled are inertial and viscous forces. To obtain viscous shear forces, we notice that shear forces are like shear stresses times the area. The shear stress is given by the Newton law. Shear stress mu dV by dy, the velocity gradient. So the scale factor for shear forces is like K mu times Kv divided by Kl. And the scale factor of area is simply KL square. And therefore, the shear force scale factor, the viscous force scale factor is K mu, Kv, Kl. And the relevant pi number is F mu divided by mu VL. Then we do for the inertial forces. And as before, the inertial forces are mass times acceleration. Mass is like rho times the volume. So K mass is like K rho times KL cubed. And acceleration in terms of V and L can be written as Ka is equal to Kv square divided by Kl, so that the relevant scale factor for the inertial force Kfi is K rho, Kv square, Kl square. And from this, we get a pi number Fi divided by rho V square L square. The two scale factors, Kfi and Kf mu, should be exactly the same. And from this, we get K rho, Kv, Kl should be K mu. Or as we have done this before, we obtain rho VL by mu as the pi numbers. For similitude then, we need to match the Reynolds number. Thus, the modeling rule is the Reynolds number for the model should be same as Reynolds number for the prototype. Since rho and mu of the model and prototype are identical, since the fluid used is the same air, the model velocity is the prototype velocity times Lp divided by Lm, the characteristic length of the prototype divided by characteristic length of the model. It says the scale factor used is 6 for the length. This gives you a velocity of the model to be 360 kmph. That is, the model should be tested at a wind speed of 360 kmph. To higher speed. But there is something in the drag forces on objects that we will just look into that permits us to test at almost any speed. But suppose it is tested at 360 kmph, Then we obtain the prediction rule for the drag, and is obtained from the force scale factor relation. Drag force is like any other force, and its scale factor must be equal to the scale factor for all forces. We may choose to equate it to any of the two force scale factors that we obtained. Setting the drag force scale factor equal to the inertia force scale factor, we get K drag is like K rho, KL square, KV square. And from this, we obtain drag divided by rho L square V square as a pi number, where L is a characteristic length and V is a characteristic velocity. This should be same for the prototype and the model. Thus, the drag of the prototype is drag of the model times LP by LM whole square. LP by LM is KL, the scale factor for length, and VP by VM whole square, scale factor for velocity. The drag force for the model was 510 newtons. The scale factor of length is 6, and the scale factor of velocity we just found out is 1 by 6, so that the value of the drag force on the prototype would be the same 510 Newton. Our model is smaller by a factor of 6, but we are testing at a velocity which is 6 times the prototype velocity, so that the force scale factor is 1, and the drag on the prototype is the same as drag on the model. The power required to overcome the wind drag can be obtained directly from the velocity and the drag, as power is equal to force times the velocity. We convert 60 kmph into velocity in meters per second, and we get 8.5 kilowatt. So this is the power that will be required by the car to drive at 60 kmph. The pi number drag divided by rho L square V square is very often used pi number in aerodynamics, though mostly with slight modification. What modification? We use a factor of 1/2 in the denominator, and L square is replaced by a characteristic area, and this is now given the name drag coefficient. When the flow in the model is similar to flow in the prototype, then the drag coefficient is same. The characteristic area depends upon the geometry. For bluff bodies like automobiles, etc., the conventionally used characteristic area is the frontal area, the area that meets the flow in the face. While for the aircraft wings, the planform area of the wing is used as the characteristic area. Thus, the drag coefficient of any geometrically similar shape is going to be the same if the Reynolds number match. That is, CD is a function of Reynolds number for same geometric shape. We plot here the drag coefficient for a sphere at various Reynolds numbers. The dots represents the measurements by many researchers on different types of fluids, different sizes of spheres, etc. And they all fall in a single curve, proving the power of the analysis that we carried out. that the drag coefficient is a function of Reynolds number, and the geometric shape is borne out completely from this graph. An interesting thing to notice, however, is that over a large range of Reynolds number, from about 10 is to power 3 to 2 into 10 is to power 5, the drag coefficient is effectively independent of Reynolds number. This fact is of great importance. In fact, you would see tables in handbooks for drag coefficients where the Reynolds number is not mentioned. The drag coefficients for a sphere in laminar flow is given as about 0.6, for a flat disk at about 1.1, and so on. Reynolds number is not mentioned because for most engineering applications, the relevant range of Reynolds number is this. So for this automobile that we had, we didn't need to match the Reynolds number. In fact, testing it at the matching Reynolds number, which required a speed of 360 kilometers per hour, would create serious problems. The speed is so high that it is tending to be in the regime where compressible effects start becoming significant that we neglected. So if we measure drag coefficient at that large a speed, we may not get the right result. So we measure the drag at any speed, a much lower speed, convert into a drag coefficient, and then using the fact that the drag coefficient is independent of Reynolds number, we say that the same drag coefficient would apply to the prototype automobile, and from this we calculate the drag on the prototype. Another example of a water pump. This water pump is picking up water from this sump and pumping it to an overhead tank. The delivery point is a distance hd. So this is the head that is being produced by the pump. A pump capable of lifting 5 meter cube per second of water against a head of 250 meter, that is HD is 250 meters, at 500 RPM is to be designed. It will be a rather big pump. So a 1/9 scale model is constructed and tested with the same fluid, that is water, against a 10 meter head, a much reduced head. At what speed should it run? And what would be the volume flow rate if we are going to get similar flows? And then what would be the power scale factor between the prototype pump and the model pump? So as before, we begin by deciding what are the important forces. The pressure forces and the inertial forces are the only ones that need to be modeled in this problem. Since this pump is a rotary machine, centrifugal inertial forces should also be modeled. That is, the centrifugal forces should also have the same scale factor as the other forces. So now we have three governing laws, one for the inertia, the second for the pressure, and the third for the centrifugal force, mass times omega square r. And r is like a length, so mass into omega square L. Omega is the angular speed. By using the process that we followed earlier, we write the scale factors for the inertial forces, for the pressure force, and for the centrifugal force. From these two, equating these two, we get the scale factor for the pressure. Difference is equal to the scale factor for the density times the scale factor for the velocity squared. So delta P by rho V square is a pi number, and we recognize this as 1 over Euler number that we discussed earlier. By equating the scale factors for the inertial force and the centrifugal force, we obtain this similarity rules that k omega times kl should be kv. And from this, we get omega L by V as a pi number. This pi number is named as Strouhal number and is abbreviated as ST. So these are the two pi numbers that must match. Now, in our problem, we match the Euler numbers. We get a relationship for Kv. Rho is the same. The ratio of delta P in the model and the prototype is given as 250 meters for the prototype divided by 10 meters for the model. And so this is like 5. That is the velocity ratio. This Strouhal number similarity, on the other hand, gives us omega L by V for the model is the same as omega L V for the prototype, which gives you the angular speed of the model should be 9/5 of the angular speed of the prototype. Since the RPM of the prototype is 500, the RPM of the model should be 9 by 5 of 500, which is 900 RPM. So when the prototype runs at 500 RPM, to obtain similarity, we must run the model, the scale model, at 900 RPM. The prediction rule for the discharge is found by the scale factor relations. The scale factor for discharge is like velocity times the area of cross section. Area of cross section would be scaled by KL square. Velocity scaled by KV. So KQ dot would be like KL square KV. KL is 9, scale factor of length, and scale factor of velocity is 5. So the scale factor for volume flow rate is 405. Thus, the model should deliver only this flow rate instead of 5 meter cube per second, which is huge volume flow rate. It needs to deliver only a very small fraction of this, 1 over 405 of that. The scale factor for power consumption is obtained from the relation power is equal to force times velocity. So K power is Kf into Kv, and Kf is like K rho, KL square, Kv square. So Kf into Kv is K rho Kl square Kv square. Here K rho is 1, we are using the same fluid. Kl is 9 and Kv is 5. And we put it all together, we get a power scale factor of more than 10,000. So prototype will consume 10,125 times the power used by the model pump. These few examples should demonstrate to you quite clearly the power of this method of scale factors, or the law approach it is sometimes called. We can work with the relevant laws and then obtain results very quickly. Another example, surface waves in deep water. The wave speed v of a surface wave in water is found to depend upon the density rho of the water, the wavelength lambda, the depth d, and gravity g. The waves are moving on the surface of water. The fluid particles are not moving. This is the speed of surface waves. In deep waters, where d is much greater than lambda, the depth is immaterial, and the speed of the surface waves depends only on rho, lambda, and g. In fact, we will see that rho should not matter, because neither v nor lambda nor g contains the dimension of mass. And so the only parameter rho which contains dimension of mass would not occur in any non-dimensional relations. Let's determine this function of rho, lambda, and g. From the list of independent quantities involved, it is easy to see that only the inertial and the gravity forces are likely to be significant. So we will invoke the law for the inertial and the gravity forces. These are the relevant scale factor relations. And if we equate these two, we get a similarity rule that Kv square divided by Kl, Kg should be 1. And from this, we obtain the pi number V square by Gl, the square of fluid number, as invariant. It is easy to see that wavelength lambda can be used at LC. However, there is no physically relevant independent parameter that characterizes the velocity Vc. So the life is simple. This V square by GL becomes a prediction rule itself. There is no modeling rule required. So V square by GL should be order 1. So V square should vary like GL. L is lambda. So V is like C times under root G lambda. The scale factor for velocity is related to scale factor for time and length, so that Vc Tc by Lc is invariant, which permits us to use Tc is like Lc by Vc. And so the time period is like under root lambda by G. This is for surface waves in water in deep ocean, where d is much larger than length. When a wave approaches a sloping beach and the depth of water d reduces to less than the wavelength lambda, the characteristic length becomes d rather than lambda, and the wave speed reduces. It is now given by v is equal to c under root gd. This is interesting. You see here in this GIF, the waves are approaching the beach towards us. The water rises, the waves rise when they approach the beach. And this is happening because the friction at the bottom of the beach slows down the waves. The wave velocity on the top is larger than the wave velocity at the bottom. So there is a bunching of the liquid and the waves rise, causing the phenomena of breaking of waves on the beach. In fact, tsunamis, which can have wave heights of a few meters, are caused by this phenomena. Tsunami waves, when they are in the open sea, have hardly any wave heights. The ships in ocean would not even notice the tsunamis when they pass. But when they reach the beaches, they rise very high. There's a very interesting video available on YouTube regarding the development of waves in oceans. This is the reference that I've given here. I recommend highly that you watch it. Thank you.